In today's lecture, we are going to see a very important concept of ferromagnetism, and in this lecture, we are going to start to deal with the problem of ferromagnetic spin waves. Actually, the concept of ferromagnetic spin waves is a very vast concept, and so it is not possible to discuss all the aspects of ferromagnetic spin waves in one video. So actually I will provide you at least two videos on this ferromagnetic spin waves, and this is our first part of the lecture on ferromagnetic spin waves. And you will see basically in this first part of the lecture on ferromagnetic spin waves the concept of the dispersion relation. Okay, and after that in the second part of the lecture we will see the quantization of spin waves and its thermal excitation. Okay, so now let us see first of all what is this ferromagnetic spin waves. Actually, you know, the cause of ferromagnetism is the coupling of spin. Okay, and if a ferromagnetic material is at a temperature, let us say 0 Kelvin, that is at absolute zero. You know, at 0 Kelvin temperature, all the spins are parallel, and when all the spins will be parallel, magnetization is at its saturation value or highest value, which is called saturation magnetization, denoted by the symbol Ms. You know all it. Okay. But what will happen when temperature is not 0 Kelvin? Definitely, if the temperature is not 0 Kelvin, then you can't imagine that all the spins will be parallel to one another. So in that very condition, definitely the magnetization in general will be somewhat smaller than this saturation magnetization. Okay. So if you are talking about a temperature other than 0 Kelvin, then magnetization is small. So I have mentioned it here. You can see that if temperature is not 0 Kelvin, then M is less than Ms, where M is magnetization and Ms is the saturation magnetization. Okay. Actually, what is the region of decrease in this magnetization? Okay. If you want to know about the cause of reduction in magnetization, you can't attribute it to the reversal of any individual spin or spins alone, while other spins remaining as such. Actually, we should let all the spins share the reversal, not only one spin, but whenever there will be a reversal of any spin, that reversal is propagated through spin to spin and all spins get reversed. Okay. So one has to consider the reversal, or you can say the excitation or precession of all the spins in the system. Okay. As you can see in this figure A, I have shown here the excitation of a single spin would not remain localized on that very spin, but it will be shared by the whole system of spins through the exchange of interaction between them. In this figure A, you can see that if you consider that this is the undisturbed position of the spin, and once it is actually disturbed or excited, then this excitation is propagated through spin to spin, just like you imagine a one-dimensional linear lattice. And if you excite any atom of the lattice or any lattice point, then that excitation or that disturbance propagate through the lattice atom to atom. Just like that here, the spin, the excitation of a spin does not remain localized to a particular spin, but once you will excite any spin, that excitation will travel through the system spin to spin. Okay, actually a one-dimensional spin system has been shown in this figure, you can see. Okay, therefore you can say that excitations propagate through the system of spin in a wave-like form. Okay, and such a wave is actually called the spin waves. Okay, as you know, any wave, all waves has are actually quantized, and we always associate any type of wave with an energy quanta. For example, if you are talking about electromagnetic wave, what are the quanta of electromagnetic wave? You know, photons are the quanta of electromagnetic wave. If you are talking about gravitational wave, you know, gravitons are the quanta of gravitational wave. And if you are talking about acoustic wave like sound wave or lattice vibration, then you know phonons are the quanta of lattice vibration. Actually, this phenomenon is just identical or just analogous to the lattice vibration. Okay, as in case of lattice vibration, the energy is quantized in the form of phonons. Just like that, in this case, the quanta of a spin wave is called magnon. So magnon is what? This is the quantum of a spin wave, magnon. Okay. So whenever we will talk about the quantization of a spin wave, definitely the quantized form of a spin wave is simply the magnon. Okay. So you can say that these are analogous to lattice vibration or phonons. Okay. Actually, when you talk about the lattice vibration, what happens in that case? Actually, in lattice vibration, you know, the oscillation, there is an oscillation relative to the position of atoms on a lattice. Just like that, in case of spin waves, the oscillations are in the relative orientation of a spin or on a spin on a lattice site. Okay. So in this figure A, actually you can see that the spins viewed in perspective, while in figure B, spins viewed from above showing one wavelength. Okay, and the wave is drawn through the ends of the spin vectors. Okay, actually here you can see the distance between two successive spins has been denoted by the symbol A, which is just lattice constant. Okay, this is lattice constant. So this problem is just identical to the problem of one-dimensional lattice vibration, and you have actually studied this one-dimensional lattice vibration in very detail in my previous lecture. Okay. So now I hope you have an idea what is this spin wave, how it is produced, how it is generated. Okay. Actually, all those things which I have just explained, I have mentioned here in writing for your convenience, and I will suggest you, and I always suggest you, to note down these things in your notebook, and that will be very helpful to write the answer of question related to this spin wave in your examination. Okay, so all these things have been mentioned here, you can see. Okay. Now, as I have told you earlier, that our basic aim of this first part of the lecture on spin waves is actually to deal the dispersion relation. Actually, we will see the classical derivation of Magnon dispersion relation in this first part of the lecture on a spin wave. Okay. So let us now try to derive the dispersion relation for Magnon. But this treatment is almost classical, so this is called classical derivation of Magnon dispersion relation. Okay. Actually, when you say that we are going to derive the dispersion relation, you have already studied dispersion relation in case of lattice vibration. Dispersion relation means what? We have to establish, or we have to obtain a relation between the frequency of the spin wave, let us say omega, and its wave vector k. Okay. So relation between omega and k is actually known as dispersion relation, or you can say k times omega, k times a, where a is lattice constant. So a relation between omega, which is frequency of a spin wave, and ka, where k is the wave vector of the spin wave, we are going to derive. Okay. Actually, this derivation is based on the idea which we have studied in our previous video on the Heisenberg explanation of Weiss field, where you have studied the Heisenberg exchange interaction concept. Actually, that idea will be utilized here to deal with this problem. Okay, and in that case, you have seen that the interaction between the spins is actually localized. Actually, when you talk about a particular spin, it is interacted with its close neighbor. Okay, not the spin situated at a farther distance. So here also we will take this fact under account for the calculation of dispersion relation. Okay, so now let us consider a spin Sp at a site P. At Pth site we consider a spin Sp, and this spin is coupled with the nearest neighbor spins, say Sp minus 1 and Sp plus 1. Okay, so if this is your Pth spin, and this is your P plus 1th spin, and this is your P minus 1th spin, then this Pth spin will get interacted only with the P plus 1th and P minus 1th spin, we will assume. Okay, actually, due to this interaction of a spin, interaction energy will be developed. And what will be the value of interaction energy, how we can calculate it, all these things we have learnt in my previous video. So on the idea which we have learnt in the previous lecture, you can say that the exchange energy of a spin Sp with its neighbors Sp plus 1 and Sp minus 1, if the interaction energy is EE, then what will be that? That is minus 2Je times Sp dot Sp minus 1 plus Sp dot Sp plus 1. Can you remember this result? You have learnt in the previous lecture. You know, here this Je is actually exchange integral. Okay. Now, this is the interaction energy. Now, you can calculate the effective magnetic field acting on this spin. You know, in general, the interaction energy is equal to what? This is minus the magnetic moment dot magnetic field. This is interaction energy. This is the general result. Okay. So if you want to find the value of the magnetic field at the site of the Pth spin, then that will be simply equal to minus E over mu P. Okay. You know, here mu P is the magnetic moment at the site P. Okay. But we also know that this mu P is given like this. This is minus G mu B times Sp. You know it. You have used this result earlier. Actually, here this G, you know, is the length splitting factor, and mu B is the well-known constant which is called Bohr magneton. Okay, and Sp is the spin of Pth site. Okay, so this expression for mu P can be used here in this equation 2 for defining the magnetic field. And so you can write that this Hp is equal to Ee over G times mu B times Sp. Here minus minus will become plus. Okay. And when you will substitute the value of interaction energy, this is Ee, which is defined in this equation 1, in this expression, what will be your result? So I have substituted here the value of Ee, which is minus 2Je times this much. Okay. Now you can see we can evaluate this equation in this manner, that Sp dot can be taken as a common factor and the magnitude of Sp will cancel because in denominator there is also Sp present. So finally you can say that Hp is equal to minus 2Je over G mu b times Sp minus 1 plus Sp plus 1. Okay. So this is the expression for the magnetic field acting on the spin, pth spin, you can say. Okay. But you know, if a spin is in a magnetic field, that spin will experience a torque. This is just saying like that when a magnetic dipole is in a magnetic field, due to the interaction between the field and the dipole, a torque acts on the dipole. Similarly, this magnetic field will exert a torque on the spin. And what is that torque? You know, torque is given by mu p cross hp. Mu cross h is equal to torque. Okay. But this torque tau acting on the spin is in accordance with the Newton's second law of motion. You know, torque is simply the rate of change in angular momentum. What is torque? Torque is rate of change in angular momentum. So this torque tau can be defined as tau equal to d dt h bar sp. Here h bar is the reduced Planck's constant. And this h bar sp is what? This is actually the angular moment, spin angular momentum. Okay, this is spin angular momentum. So here tau will be equal to rate of change of spin angular momentum. In general, I have written that torque is equal to rate of change of angular momentum, but when you are talking about the spin angular momentum, then you have to say that in present situation, torque will be equal to the rate of change in spin angular momentum. And the spin angular momentum is given by this expression. This is reduced Planck's constant times the spin sp. Okay. So you can equate these two equations, that d dt h bar sp is equal to mu p cross hp. Okay. And this can be simplified in this manner. This is dsp by dt equal to, here mu p, as you know, this mu p has been defined here. Mu p is minus g mu b times sp. Okay. So this is minus g mu b times sp. Okay. And cross hp. And this constant h bar has been written here. Okay. Now let us simplify this RHS of equation to some extent. Say this is minus g mu b over h bar times sp cross hp. But what is the value of hp? You have already obtained in this equation 3 the value of hp. And so let us substitute this value of hp here. This is the value of hp which we have already obtained. Okay. Now we will take the vector product of sp with this sum of these two vectors. Here you can see this g mu b and this g mu b will cancel out. Okay. Minus times minus will become plus, and so this is 2je over h bar times sp cross sp minus 1 plus sp cross sp plus 1. Okay. So you can say that this rate of change in sp, this is rate of change of the spin at pth at site pth. So this is equal to 2je over h bar times this much. Okay. Now this equation dsp by dt, which gives actually the rate of change in the spin or at pth site, we have obtained. Now actually we will express this equation 4 in a scalar form. And you know, for expressing this vector equation in scalar form, what we will have to do? You will have to express all the vectors in this equation present in terms of their components, and then we will equate the x, y and z component of LHS and RHS, and then this single vector equation will be splitted into the three scalar equations for x, y and z components. And how you can find the x, y and z components of the terms of the vectors present in LHS and RHS? You can see this dsp by dt. This can be expressed as dsp x by dt I, okay, and plus dsp y by dt j, and plus dsp z by dt k. Okay, we can write this much instead of this dsp by dt. And now for finding the x, y and z components of the vectors present in RHS of equation 4, what you have to do? You can express sp vector sp in this manner. This is spxi plus spyj plus spzk. Okay, and in the similar manner you can write the expression for sp minus 1 vector. This will be sp minus 1 x I plus sp minus 1 y j and plus sp minus 1 z k. Okay, now you know you can find what will be the vector product of sp and sp minus 1. Sp minus 1, you can easily find it by in determinant form. You know, here we will write I, j, k, and here the x component of sp and here the x component of x, y, z component of sp minus 1. You know it. Actually, these algebra I have not done here. I have just given you a hint how you can evaluate it. So for finding the x, y and z component, you have to evaluate the cross product of sp and sp minus 1, sp and sp plus 1, and you can do it. This is a simple thing. And then we will equate the x component of the vector in LHS to the x component of the vector in RHS, and in a similar manner y and z component will be also equated. And I have left this algebra here, and this is just a homework for you. You can do it. This is very simple concept. And so I have written directly here. You can see that dspx by dt is equal to 2je over h bar times this much. This will be spy times spz sp minus 1z plus sp plus 1z minus spz and sp minus 1y plus sp plus 1y. Okay, and in the similar manner the expression for dspy by dt and dspz by dt I have written here. Okay, I am not giving a reading here. You can see. Okay, so in this way this vector equation defined in equation 4 has been splitted into the three scalar equations which have been defined in this equation 5. Now you can see that these equations involve the product of spin components. As you can see here, there is spy times sp minus 1z, spy times sp plus 1z. So in all terms there is a product of two spin components. Okay, and so these equations are actually non-linear. But actually to solve these equations, we have to make these equations first of all linear, and then we can think about its solution. So we actually obtain an approximate solution of these equations by linearizing these equations. And how we can actually linearize these equations? Actually for this, they we have to consider that amplitude of the excitation is small. When you say that amplitude of excitation is small, that means this SPX SPY is much smaller than SP. These components are these two components we consider much smaller than SP. Okay, and apart from that, we also consider that this SPZ SP plus 1Z SP minus 1Z, that is equal to SP, and that is equivalent to S. It means instead of SPZ, SP plus 1Z, SP minus 1Z and SP, we will write simply S. Okay. And apart from this, we will also neglect the term containing the product of SPX and SPY. When you say SPX, it means SPX, not only SPX, SPX, SP minus 1x, SP plus 1x, all those. Okay. Because we have assumed that this SPX and SPY are much smaller. So their product will be more and more smaller, and that can be neglected. So taking these facts under account, now let us see what will be the equations, three equations defined in this equation 5. So let us first of all see this first equation of equation 5. Here you can see that this SP minus 1Z and SP plus 1Z both will be equal to S. You can see. So instead of these two, we will write S. So this will become 2S. Okay, 2S. And here SP minus 1Y, SP plus 1Y, the this is, and SPZ, SPZ. This SPZ is equal to S. Okay, SPZ is equal to S. So let us see. This will be 2S, and this is 2S times SPY minus S times this much. Okay, so you can take 2 as a S as a common factor, and when you will take S as a common factor, you can see this result will be 2 JES over H bar times 2 SPY, because this is 2S and this SPY is present here, 2 SPY. Okay, and S has this SPZ is equal to S, this is S, see here, and that has been taken as a common factor. So the remaining terms are these two, that will be minus SP minus 1Y and SP plus 1Y. Okay, so this is your first equation. Now see the second equation. In this equation, again, this SPZ, this will be written as S. Okay, and here this is S, this is also S. You can see. So this is 2S. So the second in second term there will be 2S times SPX. Okay, which is actually negative. So if you will take minus as a common factor, then this second term will become positive and the first term will become negative. So I have written, you can see this is minus 2 JES over H bar times 2 SPX minus SP minus 1x minus SP plus 1x. Okay, you can see. Now see the last equation of this equation 5. Since in this equation there is a product of SPX and SP minus 1Y, and you have considered that this product is so small that it may be neglected. So all the terms after taking the product will be negligible, and we can take them equal to 0. So we can simply say that this dspz by dt is equal to 0. Okay. So after making these simplifications, these assumptions, our equations becomes now linear. Okay. And if you can remember the concept of lattice vibration which we have studied earlier, actually these equations are just like the equation of motion of lattice vibration. Okay. So by analogy with phonon problem, the traveling wave solution, or you can say the plane wave solution of these equations, can be written in this manner. The solution of this first equation in the plane wave form is written as spx equal to u times e to the power iota pka minus omega t, and the solution of plane wave solution or traveling wave solution of the second equation is written as spy equal to v times e to the power iota pka minus omega t. Actually here these u and v are constant. These are amplitudes actually, okay, of the plane wave. And p is an integer, okay. This is 1, 2, 3, 4 and so on. And a is lattice constant, okay. Actually this solution has been written on the analogy of lattice vibration which we have learned earlier. Now we will use these two equations in equation number 6, okay. And for this you will have to obtain the value of dsp by dt and dspy by dt, okay. So you can differentiate these equations in 7, and you can see dspx by dt. From here you can see this will be equal to minus I omega u times exponential to the power I pka minus omega t, and similarly this dspy by dt, this is equal to minus I omega v exponential to the power iota pka minus omega t, okay. Now in the as you have defined spx and spy, and if I will ask you to define this sp minus 1x and sp plus 1x, how you can define? Actually in the light of this equation you can see sp minus 1x, this will be equal to what? This is u to the power u e to the power I. Now instead of p you have to write p minus 1, okay, ka a minus omega t, okay. And similarly if you will write the expression for sp plus 1, what you will do? Instead of this p minus 1 you have to write p plus 1. So all these algebra will be needed, and writing the expression for spx, spy, sp minus 1x, sp plus 1x, similarly sp minus 1y, sp plus 1y, all these values and the value of this derivative will be substituted in these two equations, okay. That is the equations defined here in this equation 6, okay. And then you will see there will be some common factor in LHS and RHS, and that will be cancelled out. So after the cancellation of common factor, what will be the final result? I have written actually here final result, and I have not done that algebra, but I have just given you the hints how you can do it, okay. So try to make the calculation yourself, but I will suggest you in examination you have to write these things directly, because that will be a lengthy process, just a simple mathematics but useless, Okay. So after using this in the in this equation 6, what will be our result? The first result will be minus I omega u equal to 2 jes over h bar times 2 minus e to the power minus ik minus e to the power ik times v. Okay. Now let us take 2 as a common factor in RHS. Okay. So our result will be in RHS 4 JES over H bar times 1 minus e to the power IKA plus e to the power minus IKA over 2. Here 2 has been taken as common factor times V. But you know that this e to the power IKA plus e to the power minus IKA over 2, this is what? This is cos KA. Okay. So you can say that minus I omega u is equal to 4 JES over H bar times 1 minus cos KA. Okay. Now in the same manner, when you will write the expression for dspy by dt from here and substitute the values of spy, not spy, but in this expression you have to put spx, sp minus 1x, sp plus 1x, and then again you will simplify, then you will get the equation just identical to this equation. Only you have to replace u and v by one another. It means we will write v instead of u and u instead of v. So instead of u, now we will write this v, and instead of v here, actually here there will be v also, sorry, you have to write here u. Okay. So in this way you can see we have two equations, minus I omega u equal to this much and minus I omega v equal to this much. Now these are actually the linear equations, and you know from theory of determinant that these equations will have non-zero or non-vanishing solutions for u and v. Only when the determinant of the coefficients of u and v will vanish. This is theory of determinant. U and v will have non-zero solution, okay, or non-zero values. But that will be possible when the determinant of the coefficients of u and v will be equal to 0. Now let us see the determinant of the coefficients of u and v. So you can see that the coefficients of v is here minus I omega, and coefficients of u is what? Coefficient of u is minus I omega, and coefficient of v is 4 JES over H bar times 1 minus cos k. Okay. And here this coefficient you have to write, you can take this term in RHS and that will become plus. So this is I omega. Now here the coefficient of u is this much minus this much. So this is the coefficient of u and this is coefficient of v. This will be brought in RHS and that will become plus. This will be also brought in RHS and that will become plus, and in LHS there will be 0. Okay. So this determinant must be equal to 0 for the non-zero values of u and v. Now it is very easy determinant, you can easily solve it, and so let us see what will be your result. This will be this much. Although this should be written like this. This is plus and this is minus. this is minus. You have to take, this is I omega times I omega, that will be I square omega square, which is minus omega square, okay, and minus product of this much and this much, and that will be that will be minus minus will become plus, and that will be plus 4 JES over h bar times 1 minus cos k whole square, and that is equal to 0. And you can see that we will take this omega square in RHS, and that will be plus and multiply by this h bar square, and then when you will find 4 JES times 1 minus cos k, that will be equal to h bar omega. Actually, this equation you can see relates k and omega, or you can say Ka and omega. So this is the dispersion relation, okay, how omega varies with k for spin waves in one dimension. In case of nearest neighbor interaction, this equation actually reflects, and so this is the dispersion relation, okay. Now if you think about the longer wavelength, for long wavelength Ka is much smaller than 1. Why? Because K is wave vector, which is 2 pi by lambda, okay, and if lambda is very large, K will be very small, and therefore Ka will be much smaller than 1. And when Ka is much smaller than 1, then 1 minus cos Ka, what will be that? Cos Ka or cos theta, you can say cos theta. This is expanded as 1 minus theta square by 2. 1 minus theta square by 2 if theta is very small, okay. So taking the terms up to only theta square by 2, here this 1 minus cos Ka will be equal to 1 minus Ka square by 2. 1 will be cancelled out, and so this is almost equal to 1 by 2 Ka whole square, okay. So if you are considering the limit of longer wavelength, then this in this equation 1, this 1 minus cos Ka may be replaced by 1 over 2 Ka whole square, okay. And after doing this algebra, this equation A will become like this. This is h bar omega equal to 2 JES A square times K square, okay, times K square. And from here you can see that the frequency of the spin wave is directly proportional to K square. Frequency is proportional to K square, okay. And so this is also the dispersion relation, but in case of long wavelength, and equation A refers in general the dispersion relation, okay. Now actually in this figure I have shown the graphical plot of this h bar omega over 4 JES in against of K, and you can see when Ka is equal to 0, then this h bar omega over 4 JES is also 0. But as K increases, this increases non-linearly, and when actually this Ka is equal to pi, that means K equal to pi by A. In that condition, the value of this the value of h bar omega over 4 JES has been shown equal to 2. This is its maximum value. In fact, the maximum value of this value of k equal to pi by a is the maximum value of k. Actually, this is found in case of any wave. Okay. So this is all about the dispersion relation for spin waves, and as I have told you that in our next video on this spin wave we will learn about the quantization of spin waves and thermal excitation of magnons, in case of which a very important law is discussed which is called Bloch T3 half law. Okay, and all these things we will see in our second lecture, and I hope in this lecture you have definitely understand the idea of a spin wave clearly. Okay, thank you very much.